This is our single degree of freedom system, otherwise known as the Cussons rig, and this experiment has been deliberately designed to allow us to simulate a single degree of freedom system. We have a mass which is able to freely move, which is sitting on an air bearing, which you can hear the air coming through tiny holes underneath here, and that means that this is essentially as close as we can achieve to being a frictionless system. There is obviously some resistance to motion. We have a little bit of air resistance, which is proportional to velocity. This is moving through a fluid. There is a small amount of energy absorbed in heating up and heat that's rejected from this spring here, which is providing a restoring force to this mass as it moves backwards and forwards. So we have a mass here of a known quantity. We have some information on the rig number 5 card sitting to the left hand side here, which we'll have a look at in close-up shortly. We also have a displacement measurement device over here, a magnetostrictive sensor. So as this moves backwards and forwards here, a measurement is created. This is a sensor, and we have a voltage. There's some signal conditioning and a voltage that we can measure on the oscilloscope over here. So we can see very nice sinusoidal harmonic motion, and we have some statistics being captured by the oscilloscope. It's performing some mathematical calculations based on this signal to determine, for example, the period, the frequency, which is the reciprocal of the period, the peak-to-peak amplitude, which will be of interest to us later, and an average measurement, a mean measurement for that signal. So you can see it really very closely represents a free, vibrating single degree of freedom system. We displace it from rest and we release, and we can measure the natural frequency of that system, or we can estimate the natural frequency of the system. We also have a damper here, which is a piece of copper which moves between 2 coils, and these coils can be controlled by turning this potentiometer on here to introduce some viscous damping to the system. And there are various amplitudes of damping I can introduce through the potentiometer by increasing the voltage from 0.5 amps to an amp, and even all the way up to 2 amps. When I release this mass from rest with lots of damping, we can see the effect on the oscilloscope. This is still slightly underdamped, but there isn't very much vibration at all. It decays very quickly. If I reduce the current back to an amp, we still have an underdamped system. All of these cases are underdamped system. It's a vibrating system. You can see that there are some cycles of vibration, but we have some decay quite quickly. And if I turn this to half an amp, release this one from rest, this is the least damped of the 3 damped cases. We can use logarithmic decrement to determine the amount of damping. If we stop the oscilloscope, we can save these data to disk. They're in a voltage format. We can use the information from the card here to convert those from voltages to engineering units, and we can use logarithmic decrement to interrogate the level of 2 consecutive peaks in this trace and determine the damping for the system. This system also includes with it a motor with an eccentric bearing which we can drive at a specific frequency. There's a plus or minus 3 millimeter peak-to-peak eccentricity, so the motion of this frame backwards and forwards is 3 millimeters peak-to-peak, and the frequency is given here in hertz on this digital display. And when we drive this mass at this frequency here with some damping applied, we eventually reach steady state, and we have a forced vibration scenario here. We can drive the system at frequencies which are close to the resonant frequency, which is approximately 1.7 Hertz. And there you can see lots of vibration amplitude when we get close to resonance. If we increase the damping, we will see that, of course, that amplitude reduces. And if we increase the damping even further, the amplitude reduces even further again. If we turn the damping off completely, then we will have a case where we have no damping at all and we get very high amplitude vibration up to the point where, as you can hear, the mass is actually knocking with the end stops on the air bearing. So this isn't a good situation for us to be in. In real engineering systems, there is always some damping in the system, and that prevents us having infinite response, which would be theoretically the response we would have for an undamped system when we hit resonant frequency.